This is the Pearson Edexcel January 2022 Unit 6 Chemistry, but this is the unused paper. Two papers were made, one was used, this is the unused version. So the total marks here are 50. I'll go straight to the first question. The first question says, compound X is a green crystalline. Of course, we gotta note that it's green and crystalline. It's a green crystalline solid that contains two cations and one anion and water of crystallization. So tests were carried out on X. The first question, part A, says, state what can be deduced about X from its color. Now here we cannot confirm. The only thing we know that it's green. So one thing we know that if it's going to be green, X is going to be a transition metal because, of course, most transition metals are going to be colored, or they could be colored in crystalline state. So X is a transition metal, which could be iron 2 or iron 3. These two are going to be possibly iron 2 or chromium 3. These two are going to be possibly basically green. Part B says about 2 centimeters cubed of aqueous sodium hydroxide was added to a few crystals of X in a test tube, and the mixture warmed gently. A pungent smell, this is very characteristic, or a pungent gas was evolved that turned damp red litmus paper blue. Now, we have to be very careful. Let me get another color. Anytime you hear a pungent smell accompanied with a gas that turns red litmus paper blue, there is only one gas that turns red litmus paper blue, and that is ammonia gas. And if you are trying to identify a cation that led to production of ammonia gas, that is only one cation, which is basically ammonium. And again, how do we test for presence of ammonium cation? Add sodium hydroxide, warm gently, and then test basically the gas that is evolved using damp red litmus paper. If it turns blue, that confirms that it's ammonium cation. Next, part C says a spatula measure of X was dissolved in about 20 centimeters cubed of distilled water to form a green solution Y. So, okay, portions of Y were tested. Let's see the first test. They say 1 centimeters cubed of aqueous barium chloride was added to 5 centimeters cubed of Y. And the inference was, as well as the sulfate ion, 2 of the anions that might give the same observation are. So if we add barium chloride to something, it means here we're going to form a white precipitate. Because again, if we form a white precipitate, because here they say as well as a sulfate ion, we know if this test is going to infer a sulfate ion, it means a sulfate reacted with barium. So the barium 2 plus from the barium chloride reacted with something X to confirm that sulfate was present. It means this must have been something that contained a sulfate. It could have been sulfuric acid or any other thing that contained a sulfate. And the observation that is going to be seen when that and that come together is going to be a white precipitate. Now, it's not only sulfate that can form the white precipitate in this situation. Carbonates can, sulfides can, and maybe hydrogen carbonates can. So you can see the other two anions they say. I wrote them here, and there is a possibility of course, the ethane dioate ion as well to basically to be able to form that precipitate as well. Next part says 5 centimeters cubed of dilute hydrochloric acid was added to the reaction mixture in C1. So here the other side they say a sulfate ion is present. If you add HCl, hydrochloric acid, to something that is already made, of course, there is going to be no change because once the white precipitate is already formed, there is no change that can occur. So no observable change. There is no bubbling or nothing. So that's it. We go to the next part of the question. Okay, part 3 says, a few drops of sodium hydroxide were added to 5 centimeters cubed of a fresh sample. This is fresh sample of Y. Then they say observation, a green precipitate form that remained unchanged on standing. This is very significant, this part here. If they say it remained unchanged on standing, that rules out iron 2 plus, because iron 2 plus on standing, it's going to form, of course, iron 3 due to oxidation from oxygen in the air. So that rules out. So if we had two green possible green cations in the beginning, which was iron 2 and chromium 3, now we can confirm that the cation present is actually chromium 3. Then we go on to see sodium hydroxide solution was added to the mixture of from CU3, a little at a time. Okay, this is dropwise until there was no further change. This is in excess until excess. Okay. Then they say the green precipitate dissolved to form a green solution. So they want you to write, this is sodium hydroxide, so you expect not complete ligand substitution, but actually further deprotonation. Of course, when you add sodium hydroxide onto maybe hexa aqua chromium 3, you're going to see a deprotonation first, and then further deprotonation to create something that looks like this. So this is the formula of the basically the ion responsible for the green solution. Next part says hydrogen peroxide. Of course, anytime you see something green in a previous maybe kind of question, and then followed by hydrogen peroxide being used, you're going to see that is going to be chromium 3 being converted to this one here, which is of course chromate 6. So hydrogen peroxide solution was added to the green solution from C1V, and the mixture was warmed. A yellow solution, a green solution turned yellow. Yep, green to yellow. That is going to be Cr3 plus to Cr O4 2 minus. So this is, of course, we use hydrogen peroxide because it's a strong oxidizing agent. Oxygen in air cannot further oxidize chromium 3 to chromium 6 or chromate 6, so this is not possible. This is the only way using hydrogen peroxide which is going to be the oxidizing agent. So the ion responsible for the yellow color of the solution is going to be that. We go on to the next part, which says dilute sulfuric acid was added to the yellow. Now this one here, yellow solution. Now this reaction here is not redox, but it's going to be converting CrO4 2 minus plus H plus, giving us, we're going to produce, this is a reversible reaction, so we're going to produce dichromate like that. This is going to be to that and that. So let me see, we have to put a 2 here as well. Oxygens are 8, yep, hydrogens are 2, and then, yeah, something like that. So here we see the ion responsible for the orange color of the solution is going to be, of course, that. Next part, state what can be deduced from the observation in C3 that the green precipitate does not change on standing, and justify the answer. So here I said, of course, ion 2 cannot be the cation, because if we had something like that, it cannot be precipitated, and since it would have turned brown or reddish brown on standing. Remember, if you have ion 2 plus, if you expose it to oxygen from the air, it will be oxidized to ion 3 plus. This is going to be green, maybe in this case it was a green precipitate, and then it's going to turn into a reddish brown precipitate. So basically, yeah, that is the answer to that part. And lastly, give a possible formula of X. Word of crystallization is not required. Now, since in here we had chromium, I'm going to write it here. We had chromium, we had ammonium, and then we had sulfate. Remember, sulfate is going to be 2 minus. Ammonium is going to be plus. So we have to find a way of writing, and this chromium, of course, it was chromium 3, so it's going to be 3 plus. We have, so it means here we have, let me get a different color. We have 3 possible cations, or 3 it's going to be the total cations have a charge of 4 plus. The anion has a charge of 2 minus. So it means the anions are going to be twice. So here we see, it can be, we have to increase and make them like that, at least like this. There is that possibility. It means we need more sulfate than stated here. So to try and balance that, you can create something like this: chromium, ammonium, SO4, bracket 2, or you can create multiples of that. It's possible. Any of these would be acceptable as an answer. Let's go to question 2. Question 2 says, compound P is a white crystalline solid. The percentage composition by mass of P is carbon 60.87%, hydrogen 4.35%, and oxygen 34.78%. The mass spectrum of P has a molecular ion peak at mass to charge 138. So they say determine the molecular formula of P using all this data. You must show your working clearly. So they've given us that in P we have, let me use here. So in P we have carbon, we have hydrogen, and we have oxygen. The percentages are like that. So you see percentage composition, 60.87, 4.35, and 34.78. I get the atomic mass of each. Carbon is 12, hydrogen is 1, and oxygen is 16. So when you find the number of moles by dividing the percentage composition by mass by the, of course, atomic mass, this is the same as well. And here we get this as the number of moles of each. However, we need to find the mole ratio. Mole ratio, to find the mole ratio, you divide through by the smallest number of moles. So that divide by that gives us 7. That divide by that gives us 6, and that let me do this. I think that divide by that gives us a number that we can multiply to create a 7. So if you use a calculator, this divide by that, you're going to get a number here, but it's not going to be a whole number. So when you multiply, you will get a ratio of 7 to 6 to 3. Again, after dividing, then you will get a ratio of that to that to that, and then multiply through to get the smallest whole number ratio, which is going to be 7 to 6 to 3. So we can use this to find the empirical formula, which is going to be carbon 7, hydrogen 6, and oxygen 3, which is this. Now in here they gave us that the mass to charge ratio is 138. So to use the empirical formula to find the molecular mass, we can put this and multiply it by n, equate it to 138. Substitute 12 for carbon, 1 for hydrogen, and 16 for oxygen in here. Multiply, so we get 138n, which is 138, and gives us n is equal to 1. So here we can know that the molecular formula is actually equal to the empirical formula, so which is carbon 7, hydrogen 6, and oxygen 3. We go to the next part of the question. Part B says, samples of P are subjected to a series of tests. When a spatula measure of P is added to a solution of sodium hydrogen carbonate, vigorous effervescence occurs. So you guys know sodium hydrogen carbonate as well as sodium carbonate, if they're added to anything and effervescence occurs, that thing should be an acidic, it should be an acid basically. So this is proof of acidity. Now, again, to go back here, they said this was a compound of carbon, hydrogen, oxygen. So it means this is not an inorganic acid. So not inorganic acid because it contains carbon, hydrogen, oxygen. So it confirms organic acid, which is basically a carboxylic acid. It confirms presence of that group. So the next part says, when a spatula measure of P is added to a cold solution of acidified potassium manganate 7, the color of the solution does not change. Now you guys know, if the color of the solution changes, then it will confirm presence of a carbon-carbon double bond as in alkenes. So because the color did not change, it means there is no carbon-carbon double bond as in alkenes. Next part says, when a spatula measure of P is added to a dilute solution of bromine water, so here we see the solution turns colorless and then a white precipitate forms. This is very important. I know we use bromine water to test for presence of carbon-carbon double bonds in alkenes. However, in here, if you add bromine water, the solution turns colorless and then a white precipitate forms. This is very unique to phenol. Phenol is the only thing that is going to do that, so that is unique to that. So it confirms presence of a phenol group. And lastly, when a small stamp of P is ignited, it burns with a smoky flame. Of course, this shows us that the carbon to hydrogen ratio is like basically almost 1-to-1, or so it means there are few. The hydrogens are not so many in this specific compound. So usually, this is going to confirm an unsaturated compound. So any unsaturated compound that is not an alkene. Of course, your syllabus doesn't cover alkynes, so if it's not an alkene, it means it's going to be maybe an arene. So this part confirms presence of an arene. So they say, state what can be deduced about P from all of the tests and justify your answer. So here again, this is what I've already said. We can conclude that here, effervescence with sodium hydrogen carbonate confirms presence of a carboxylic acid. Like I said, sodium hydrogen carbonate can be used to confirm any acidity, whether inorganic acid or organic acid. But here we already knew the molecular formula of this, and it showed us it's an organic compound. So organic compound that is an acid should be a carboxylic acid. Then the next part was with potassium manganate 7. Of course, no color change showed us that there is absence of carbon-carbon double bond like in alkenes. A reaction with bromine water Our decolorizing of bromine water accompanied by formation of a white precipitate confirms a phenol group. Yep. And then burning with a smoky flame confirms presence of an arene. Here I included that since we already know that it's not an alkene and confirm it has a phenol. So it's basically an arene. Let's go to the next part, which says, describe how you would ignite a sample of P to show that it burned with a smoky flame. Here, remember, we are interested in looking at the flame, so it means the sample you are burning has to be burnt from above. If you're putting it on a surface like this, it has to be the sample put here, and then you're burning it from above. Burning it from below, you may not be able to observe the flame. So here we can see I said place the sample in a crucible. Yep, this could be a crucible or something you can see here. I drew the sample. You have the whole thing I did. So you put a crucible. Of course, it's going to be on a tripod stand that has a wire mesh on it. The sample is in a crucible, and then you torch it or burn it from above so that you can be able to observe how the flame is going to be made. So here, place on a tripod stand or a pipe clay triangle, and then ignite the organic substance P from above the crucible using a Bunsen burner. This was a 3-mark question. However, you would have got that, and that if you had mentioned these key statements in this question. So this is how you can see how the setup can be. If you could draw and then get maybe 1 or 2 marks from the drawing, and then the little explanation can also give you 1 extra mark to add up the 3 marks that were required. Next part, C says use the information from A and B to draw 3 possible structures of compound P. Now, we have to include, remember from our conclusions or from the data they gave us, we know it's a carboxylic acid and it has a phenol group. So you begin by drawing a phenol. That is a carboxylic acid. So again, we know it had 7 carbons. Carbon 7, hydrogens I think were, hydrogens, let me go back a bit. Hydrogens was 6, so, okay. 7 carbons, 6 hydrogens, and then the oxygens I think were 3. So it means, okay, so we have 1 here, 2, 3, and that is the 4th hydrogen. So we need to create, if we have a 5th here, it means that 6th is going to be somewhere. So in this case, we already have 6 carbons in here. To create a 7th carbon, it's going to be that, basically that. So it could be on this position, position 1, position 2, or position 1, position 3, and position 1, position 1, and position basically 4. Again, to show you something else, another student could think, why can't it be like this? Because that and that are actually the same. Also, this and that, OH, and then that and that are actually the same. So it means whether you had represented this one here or that one, it's if you had put this and that or this or that, you get the same mark, or that is same mark, but this is unique, it's going to be different. So the ones I put here are the 3 possible structures that you could be looking at. Let's go to the next part of the question. They say the infrared spectrum of P is shown. One of the peaks has been circled. Now be very careful about this peak that has been circled. If we can see, it's about at 750, about there. So let's look at the questions that follow. They say the infrared data for some organic compound, organic functional groups is as below. Okay, and then they say explain how the circled peak in the IR spectrum and the table of infrared data may be used to deduce the structure of P. Now you remember we saw the peak is at 750, so it could be 750 this or 750 that. But to confirm presence of this, it should be at this point and at 700. Or for this part. So basically, it could be this or that, but for it to be this, there should be a peak at 700 too. I'm going to go back to my graph and see, to my the infrared spectrum and see, there is no peak at 700. If I draw a straight line, you're going to see that this is not at 700. You can see that. It is below 700 because 700 is actually here. That is where we have 700. That is 700. So there is no peak at 700. That means that it cannot be this. So the only possible structure is going to be this. So it's going to be an arene with four adjacent hydrogen atoms. So it means, remember we had three possible structures. The only arene, or the only product that has four adjacent carbon atoms, is going to be this, because 1, 2, 3, 4. Sorry, 4 adjacent hydrogens. There is a hydrogen here, closer or adjacent to the next hydrogen, adjacent to the next hydrogen, and adjacent to the next hydrogen. So these 4 hydrogens are adjacent. The other structures are like the structure like this one here. Let me see, OH, and then CO, OH. It has a hydrogen here, hydrogen there, and there, but they are not close to each other or adjacent. So this one doesn't have 4 adjacent hydrogen, or 4 adjacent hydrogens, so it's only this structure. So here I say the wave number of the circle peak is at 750% meter. It has 4 adjacent hydrogen atoms, and the structure is only possible if OH and COH are on adjacent carbons. So let's continue to the next question. So question 3 says, iron 2-ethane dioxide is an orange solid which is only slightly soluble in water but dissolves in dilute acid on heating. The formula of the compound, of course, is given as that. Let me use a different color here. So where X is the number of moles of water of crystallization, the number of moles of water of crystallization in that may be determined by titration, and the procedure is, of course, step 1. Accurately weigh approximately 2 grams of iron 2-ethane dioxide into a 250 centimeters cubed beaker. Then step 2, add about 100 centimeters cubed of this dilute sulfuric acid to the beaker and heat the mixture until the solid dissolves. Part 3, step 3 says use the solution prepared in step 2 to prepare 250 centimeters cubed of iron 2-ethane dioxide solution and fill a burette with a standard solution of potassium manganate 7. Step 5, transfer a 25 centimeters cube portion of the iron 2-ethane dioxide solution to a conical flask and heat it to about 60 degrees Celsius. Then titrate the hot solution with the potassium manganate 7 solution. And step 6, repeat step 5 until concordant results are obtained. The half equations for the reactions are basically this. So the first part says describe the procedure in step 3. Step 3 is here how you convert the solution that has been made, the 100 centimeters cube solution of dilute sulfuric acid. You use them to make a 250 centimeters cube solution. So here we will transfer the 100 centimeters cube solution into a 250 centimeters cubed volumetric flask. Yep. And then add dilute acid. Of course, you remember after you transfer the solution, you have to transfer the washings as well. So from the beaker, you add in a little dilute sulfuric acid, swirl, and then transfer the washings to the 250 centimeters cube volumetric flask. And lastly, after transferring, you have to top up. If this is our volumetric flask, I'm not that good at drawing, and this is the beaker. So in this beaker, you had 100 centimeters cubed. So you will transfer this here. Of course, you're going to have a funnel here. You transfer that there, and then you add some acid in here, swirl, and then transfer the washings to the other side as well. And then after that, you will add some dilute acid in order to top up to 250. Of course, you have to shake to ensure or mix properly to ensure that the solution created has uniform concentration. Okay, shake or mix to ensure uniform concentration. Yeah, so that's it. Let's go to the next part of the question. It says, state the color of the solution at the end of the titration. Of course, it's going to be pale pink at the end of the titration. Next part says, in an experiment, 2.02 grams of iron 2-ethane dioxide was used to prepare the solution and potassium manganate 7 solution of the concentration. So let's see. This is the mass. Everything is very important here. This is the concentration, and then this is the volume used. Now, since we are using the iron ethane dioxide, and then we are using potassium permanganate or potassium manganate 7, we have to make sure we understand what we're dealing with. So I began by breaking it down. If this is 1 mole of the iron ethane dioxide, it's going to produce 1 mole of, because this is iron 2, of course, it's going to produce 1 mole of, there is 1 mole of iron 2 and there is 1 mole of ethane dioate, as you can see it here. Now, if these two are released in solution, the iron 2 is going to react through an oxidation reaction like that, releasing 1 electron, and on the other side, the ethane dioate is going to react in this way, releasing 2 electrons. So the total number of electrons released are going to be 3. Now, when we come here, it means this is going to react to produce iron, 2 carbon dioxides, as you can see here, and the total 3 electrons. I combine that and that. We have the iron, this thing here on one side, producing that and producing that, which are basically here. And then, of course, the manganate is going to be easy. Manganate produces manganese too. So it means these are the 2 half equations we're dealing with. And first, you remember, if there are 3 electrons here, I'm going to use a highlighter. If there are 3 electrons here and 5 electrons here, we have to ensure that since this is a redox reaction, these are 2 redox half equations. So total is going to be, of course, a redox reaction. We expect the number of electrons released here to be the same as the number of electrons that are going to be consumed here. So to ensure that a 3 and 5 kind of generate the same thing, multiply this equation all by 5 and this equation by 3. So when we do, we create this equation here. So you can see we have 5 ethane dioate, 5 iron ethane dioate, 5 iron 3. Then we have 10 carbon dioxide and 15 electrons here, 3 manganate 7, and then 24 iron H plus and 15E, 3 Mn2 plus, and then 12 water. So these are the 2 full half equations after the electrons have been multiplied basically, or have been made into the right number. So here I put the information. They told us the mass of this was 2.02 grams, and here the concentration was 0.0195, and the volume was that. So since I know all the information for this, I'm going to begin with that by finding the number of moles of manganate 7, which is concentration times volume. Again, remember this volume is in centimeters cubed, so we divide it by 1,000 to convert the volume into decimeters cubed, and these are the number of moles we get. Now, when you look at the mole ratio of this to that, it's going to be 3 to 5. So if we want to find the moles of this, we can say 5 divided by 3 times the moles of this. So 5 over 3 times the moles we've got here gives us those moles. But remember, these moles are in 25 centimeters cubed. To find the number of moles in 250 centimeters cubed, you're going to multiply the number of moles you got here by 10, because you're scaling up from 25 to 250. It means those in 25 have to be multiplied by 10 to get those in 250. And now, since we have the moles of this in 250 and we were given the mass initially, so we can be able to find the molar mass, which is going to be 202 mass divided by number of moles, and we get that as the molar mass. Now, the only thing we're looking for is the the number of moles of water crystallization. So this whole thing should give us that. So iron 2 is, of course, 55.8. Each of the carbons is 12, so twice of that is 24, and then each oxygen is 16. Times 4 gives us 64, plus the full water is 18, so 18x gives us that. We find the value of x. The value of x was found to be 2.09. However, this has to be a whole number, so you cannot leave it like that, so x should equal to 2. The number of moles of water crystallization should be 2. Next part says, another experiment followed the progress over time of the reaction of ethane dioate ions with manganate 7 ions in an acid. So the results are shown below. Actually, this is just a graph. I'm going to use this on the next part of the question, so you be very careful. If you observe this, the reaction is kind of slowing down. It's kind of slower at the beginning, then it's going to be rapid until it flattens out here. This looks like an autocatalyzed reaction. However, we can confirm in the next part of the question. So here they ask, describe in outline a continuous remember, this is continuous monitoring method for obtaining results such as these. Practical details are not required, but any essential apparatus should be named, and the means of obtaining the concentration from measurement should be obtained. Now, previously, they have carried out the titration experiment, so it means we cannot use titration here. So for me, I got, since gas is going to be produced, which is carbon dioxide, using a gas syringe, we will collect the carbon dioxide produced, and then we can use the molar gas volume equation to convert the volume of carbon dioxide produced into number of moles, and then these moles, so basically the moles of manganate can be generated from that, because we're going to find the number of moles of carbon dioxide and then use the mole ratios to find the number of moles of manganate, and so then the ratio will be used to find the number of moles of this, and later we can obtain molar mass. Another thing could be you measure the change in mass. Of course, you remember, anytime a gas is produced, we can monitor the reaction by measuring the change in mass or by collecting the volume of gas produced. So in this case, you could also measure the mass, the change in mass over time by carrying out the experiment on a balance, and then you can be able to know the mass that has decreased and then use that in the calculations here. You can use number of moles is mass over molar mass equation to convert, of course, the mass of carbon dioxide lost into moles of carbon dioxide generated, because the mass decrease, I want to say the mass decrease, this is going to be the mass decrease. So the mass decrease is going to be due to carbon dioxide that comes up, and that means that will be the mass of carbon dioxide. And since we will know the mass of carbon dioxide and we know the molar mass of carbon dioxide, we can be able to get the moles of carbon dioxide and then work around with the reaction equation with the mole ratios around the two equations to be able to find the number of moles of that, and then later use it to find the molar mass, of course, the molar mass, and then the value of X. So in the next part, they said determine the rate of reaction at point A and at point B. You must show you're working clearly on the graph, point A and point B. If we go back to the graph, we can see there is a point A here. Let me use this. There is a point A here and a point B here. All we need to do is draw a tangent at that point and a tangent at this point and find the gradient. Now, different students are going to draw different tangents, but for me, when I drew the tangent here and the tangent here, of course, this is like a straight line, so I didn't need to draw a tangent. I got the points that were easy for me to obtain, which was that, and I used those here to find the gradient. I also got this point here and that point here, and I used them here to find the gradient. So I have two gradients. If you observe these two gradients, this here is smaller than this one here, meaning the rate of reaction here is lower than the rate of reaction here. So those values, I transfer them here. You can see that and that. And finally, they ask us explain why the values obtained in B2 are different from the values of a typical rate experiment. In a typical rate experiment, usually the initial rate is going to be the highest because you have more reactants within the same within more number of moles of reactants, so they'll collide more frequently, and the rate is going to be highest initially. However, in this case, the rate increases as the reaction progresses, and this is typical of an autocatalyzed reaction. So I said, in a typical experiment, the initial rate is the fastest. The initial rate. However, here the rate of reaction at A is slower than that at B. This is an autocatalyzed reaction, and the product Mn2 plus catalyzes the reaction, so the rate speeds up as the reaction progresses. Question 4. Here we have, they say, the identity and purity of an organic compound may be checked by measuring its melting temperature. Students were asked to determine the melting temperature of samples of a solid organic compound using the apparatus shown. So here we have a fuel tube, we have a thermometer here, and we have a capillary tube, Bunsen burner, we have a beaker, we have rubber band, and we have a solid sample on a watch glass. So we are trying to determine the melting point or the melting temperature. Here you have to be very careful because you have to use every apparatus given here, or at least everything. So let's go to C. So for me, I got the fuel tube. Remember here we were given the beaker containing mineral oil. The mineral oil is what is used. So basically you heat the fuel tube containing mineral oil, and then in there you position your sample basically. So the sample is going to be in a tiny capillary tube. However, you guys, the capillary tube looks like that when you buy it. So what you have to do, you will heat it on a flame it a little so that it softens, and then you can seal it like that. You manually seal it, and then after you can use a tiny sharp object to insert the sample in here, something tiny, so that the sample goes down there. So, and then in there, of course you're going to take that part out. After the sample has been inserted inside here, you can see it's going to be similar to what we have here. This part here, you can see, we see the capillary tube, containing the sample inside there, and then you position the thermometer side by side along the capillary tube. Remember, the bulb of the thermometer and the position of the sample in the capillary tube have to be close to each other, and then use the rubber band to tighten them together so that they do not separate. So here we have the mineral oil filled in here, and then of course we have a thermometer, the rubber band tightening them together, the capillary tube and the sample, and then the mineral oil in here, and then you hit this position. Please do not hit here. This position is far away from the sample, so when you hit it, it allows time for the heat to spread to this side and that side. By the time it reaches here, it means it's kind of evenly heated, so you can be able to determine the correct temperature. So in words, I said use a Bunsen burner. Of course, the Bunsen burner. You have to describe the whole process, how you seal the capillary tube, how you put in the sample. If you want to get 5 marks, you gotta go all the way. So using a Bunsen burner, heat and seal the capillary tube, and then transfer the solid into a cold tube. Of course, if it's a hot tube, of course, the sample could melt, right? Into a cold tube, tapping gently for the solid to be directed to the bottom of the capillary tube. Yes, it has to be at the bottom. And then you fill the fill tube with mineral oil. Of course, so it has to be filled to slightly, of course, higher than the upper arm. The upper arm is about here, so higher than the upper arm, and with clear mineral oil. And then next, using a rubber band, tie the capillary tube to the thermometer, ensuring that the bottom of the tube is near to the thermometer bulb, which is here. Thermometer bulb, bottom of the tube, they have to be close to each other. So you then insert them into the fill tube. Of course, the fill tube already has the mineral oil in here. So then we heat the fill tube on the side arm with a Bunsen burner, and then note the temperature when the solid melts. Of course, you'll be observing. That is why you have to use clear mineral oil, so that you can be able to observe when the solid melts into liquid, and that you read the temperature from the thermometer when that happens. So lastly, here they say state how the melting temperature of an impure. Here, this is an impure sample of an organic compound will differ from that of pure compound. An impure sample, its melting temperature is going to be lower than that of a pure sample. So, of course, it's going to be lower than that of a pure sample. Yeah, basically that's it. So this brings us to the end of this paper. Of course, this is the January 2022 Pearson Edexcel Unit 6 chemistry paper. This is the unused paper. I think students did not take this paper. So I'll see you in the next video when we talk about the other Unit 6 paper that was used by the students.